So in this lecture, I really want to talk about a few more calculations with these 1 over R, 1A cyclic quotients, singularities. So I'll say again what they are and so on. I want to talk about the discrepancy. So in other words, when I do one of these resolution of singularities, I want to know ky equals kx and then maybe plus sigma ai ei, and I want to know who. So what are the ai? Okay, that's one point. Another point is this r over a versus r over r minus a. So I had this, I had both of these in the first lecture and the second lecture. I talked about both of these different fractions, and you know, it's sort of surprising that for one class of varieties, I have to use these two different fractions. And what are they? What's the relation between them? And so it turns out that they sort of basically come from continued, I'll explain this, a continued fraction expansion of 0. So this is very elementary, but it's something that turns up again and again. It turns up in many different places. Right? And then the last thing I want to talk about, which I'm going to talk about first, is deformation and degeneration. So the many other aspects of this but I'm just going to talk about this. So in the second, in lecture 4, I'll talk about Duval singularities and threefold terminal singularities. So I'll talk about this rather quickly because I don't intend to do very much with it. Just on the other hand, it sort of comes out naturally from the same ideas that I've been talking about. So let me start on this little game of doing deformations. So recall I had this picture. So 1 over r, 1a. So here 0 is less than a is less than r is coprime. So r is some number and a is coprime to r. And this means C2 with the action of mu r given by so C2 maybe with some coordinates, probably not consistent. So u goes to epsilon u and v goes to epsilon to the power of a v. Okay, remember, so epsilon here is a particular root of unity, so it's any element of the group of roots of Rth roots of unity. So I had this picture, x0, x1, and then, well, let me draw it sort of realistically, the one I want, x2, x3, x4. I think x4 is down there. Right. So remember, I said I'm going to start off with x to the power u to the power of r, obviously invariant, and then I'm going to write down u to the r minus a times v, and then I'm going to continue. Right. And x I'm going to have xi minus 1, xi plus 1 equals xi to the power of ai. And ai is, and the ai here are continued fraction expansion of r over r minus a. This is a1, a k minus 1. Right, and the picture I'm drawing here is this 1/19th of 1/8. So I'm writing down 19 divided by 11 is 2, 4, 3. Right, so here I've got, so you know, just this is just a particular case, but so here I've got u to the 19th, and then I've got u to the 8th v, and if I try to go in this direction one more, this 8 here is less than 1/2 of 19. So if I try to continue this in an arithmetic progression, I'll go outside the box, right? So I don't do that. I take x1 cubed and then times x2. Hey, that's good. Yes, so I'm going to take this guy cubed minus this, and I'm getting u to the 5th v cubed. And then I'm going to get, I hope I've got this right. Then I'm going to get this to the 4th, 19 over 3 is, maybe I should have done the calculations properly. It was right first time. It was right first time. So what am I doing wrong? It's strange. The thing I want to write down is x0, x2 equals x1 squared, x1, x3 equals x2 to the 4th, and x2, x4 equals x3 cubed. Right, so I thought I had it right, but obviously I haven't. Oh, I'm sorry, this is 11. And then just continue this. Okay, what I said was sort of more or less right, but and then x3 is u to the, so I have to do 4 times this. This is u v to the 7th. And then okay. So I should have drawn these in a straight line, and then there's a sharp angle here, and then there's a less sharp angle there. Right, this is 4, this is 3, this is 2. Okay, so now, so this is just an example, but I could do it with any number of these. And I want to make a point that I can, so instead of this, so instead, I want to consider an open tent looking like this. Yeah, so the thing I want to write is I want to choose S1 and S2 here. So S1 is x0, x2 equals x1 squared, and S2 is x2, x4 equals x3 to the 4th. Right? So these are 2 different cyclic quotient singularities. As you can see, they're both of the simplest possible type. They're these just hypersurfaces here. So this is a half of 1, 1, and this is a quarter of 1, 3 in some notation, right? But I want to glue them together along this x-axis, x2 axis, right? So this picture here is in A5 with the same coordinates, x0, x4. Right? And in addition to the equations that I've written down here, which are nice, reasonable equations, I'm also going to write down that x1, x3 equals x1, x4 equals x. So all of the ones that are not in the same component, so x0, x3 equals 0. x2, it's wrong. x0, x4 equals 0. Yeah? So I'm in 5 space. I've got this thing here which is a surface, and it's a union of 2 components. So one of them is contained in x0, x1, x2, 3 space. So there are 2 A3s here meeting transversely along an axis. And inside here I've got one of them, and inside here I've got the other of them. And they're just meeting transversely there. Right? And so, you can ask, what is the deformation theory of this union? So this union is a non-normal, a reducible variety, but it's still in an obvious way a toric variety. All the equations here involve only monomials, right? And you can ask, given this variety, how can you deform it? Well, this axis you should think of as being a non-isolated locus of singularities, and therefore, so the x2 axis is locally x1, x4 equals 0, x1, x3 equals 0, right? So, this is really, if you think of x1, x3 equals x2 to the n as n plus 1 as the an singularity, then this one is the a infinity singularity. All right? And, how do you deform this guy? Well, because it's non-isolated, the deformation theory is infinite dimensional. Right? It's infinite dimensional, however, it's a toric variety, so the deformation theory of this singular locus, of this non-isolated ordinary double point, is infinite dimensional, but graded, and one dimension in each degree. Right. So the game I propose to do is to choose some number here. So choose one graded component of this, and the one I'm choosing here is this 4, and see if I can take this surface and move him a bit to smooth out this locus. Right. So I want to do x1, x3 equals 0, deforms to small deformation to x1, x3 equals some deformation parameter a times x2 to the 4th. Right? So I could do it with some numbers other than 4. In fact, I could do it with even 1 or 0 or negative numbers. But at the moment, I just want to do this, right? And so it turns out that, so can we do this? So if you think about this, you know, let me sort of draw x0, x1, x2, x3, x4, right? And I want to say, right, I'm going to put a tag here, a tag 4 here, and a tag 3 there. And I'm also going to add this thing which we're going to call annotation. So it's this deformation parameter there. So in other words, can we find an affine toric variety? So I want it to be irreducible with these equations, with these parameters and equations. And the answer is obviously yes. Right? So namely take x0. So I want to take here a5 x0 up to x4, and then times a1, and this is with coordinate a. So this is really a deformation parameter, and these are the toric parameters. Later I'll set a equals 0 to get back this picture, and a equals 1 to get back this picture. Okay, and so then I'm going to say I want to have x0, x1, and a are a basis for a toric lattice M, and then I want to say x2 is x1 times x0 to the minus 1. X3 is, so I'm just taking this equation here, and I'm taking this equation here as the definition of x3. So I'm going to take x3 to be a times this x1, x0 to the minus 1 to the power of 4 divided by x1. Right? And you can all do the calculation. This is a x1 to the 7th over x0 to the minus 4. And then I want to do x4 equals x3 cubed over x2, and that's similarly a cubed x1 to the 19th over x0 to minus 11. Okay. So what I've got here is I've got some, this is a lattice M. Now it's a three-dimensional lattice M. Right, and I've got some monomials in there, and I just take the convex hull, and I say, right, that's going to be a toric variety. And then these equations will hold. These equations here hold just by definition, and then maybe these equations don't define an irreducible variety, and so I just make them define an irreducible variety. So I throw in, so plus other equations to make it, well, so irreducible toric. So in other words, I just write down all the equations that hold between these monomials in this lattice. Right, and it turns out that the additional ones I've got are x0, x3 equals x1, x2 cubed a, and x1, x4 equals x2 cubed x3 squared a, and x0, x4 x2 to the 6th x3 a squared. So basically we're not interested in these equations. These equations follow from the others by the assumption that in this new variety, x0, x1, x2, x3, x4, and a are not zero divisors. I want this to be an irreducible variety. So you know, if I do sort of some kind of syzygy combinations of any two equations, I can do a little bit of cancelling and I get these. Yes? So this gives the upshot of this is, now that I have So this gives a flat deformation family. So I've got sort of S, maybe curly S, over A1. And this is the guy with the coordinate A. Let me write this curly S. Right, and in here I've got S naught is this thing here, S1 union S2, so this is a reducible. So this is an open tent. And then maybe I shouldn't say S naught, SA equals 0. And SA equals 1 is 1/19th of 1/8, irreducible. Okay? So, well, you know, I mean, this is just a little, an obvious little point. Whenever I have these, whenever I have these equations here, I can view this as a kind of excuse. I can put in deformation parameters here, wherever I like, AI, you know, whatever I want to do, and make and view this, the quotient singularity I started with, so this thing here, as something that's appearing from a deformation family of these open tents. Okay, so I want to do this. The reason I'm doing this now is because later on I'll be doing deformation of closed tents, and it's sort of basically using the same idea and the same language. Okay, so that's one topic. This is just I'm not going to say anything more about this this week, this time, but maybe next time, and when Gavin Brown is here, we'll be discussing a lot more constructions being made using this. Okay, so now let me talk about this R over A versus R over R minus A. Right, so you already saw me make the mistake of 1/19th of 1/8. Then I have this x naught is u to the 19th, and x1 is u to the minus 8, u to the 11th v, and so on. And so, and I'm getting this. I'm getting this r minus a as the beginning of this continued fraction algorithm, right? Whereas, so I have lattice M, monomial lattice M, and that has these, I'm thinking of starting there with x naught and then x1, right, and going down there, and then there's the lattice of weights, which is called L. So this one is this one, which is the Z2 plus Z times 1 over R 1A. And here I'm using, you know, it's exactly the same calculation, but it's a slightly different notation. So here I'm saying this is the point 0,1, this is the point 1,0. It's sort of supposed to be dual to this picture in some sense, and then this 1 over R of 1A is there. Right, and the point is to understand this lattice and the over lattice L. Right, whereas this was a lattice of invariant monomer, so it was a sublattice. So what's the relation between the two continued fraction exponents? So it's given by the following thing, that if R over R minus A is A1, A2, K minus 1, and R over A is B1, B2 up to BL minus 1. Right, this is the notation I've used so far. Then, if I do this, continued fraction expansion of, so I'm going to write down these guys here, but in inverse order, because I want this A1 there to be in the middle. Right, so I'm going to write down A, K minus 1, A, K minus 2, A, 2, A, 1, 1, and then B1 up to BL minus 1. So I told you earlier that when I have these continued fraction exponents, I always assume the guys here are greater than or equal to 2. So here I'm breaking this rule here. So this is, what I'm doing here is I'm concatenating two continued fractions. And these are genuine ones with all the AI and all the BI greater than 2, right? But I'm putting with a 1 in the middle. Right, and the answer is that this is 0. You know, what's a continued fraction expansion of 0? So let me give some examples. And, you know, if you want to understand this, you start off with something which is not really an example. So if I write down 1, comma 1, right, this is 1 minus 1 over 1, and so it's 0. Yeah, nothing very surprising there. Right, so let's do another one. 2, 1, 2. Right, so this is 2 minus 1 over 1 minus a half. Right, so this is 2. So, you know, 1 minus a half is a half. 1 over a half is 2. So this is 2 minus 2 equals 0. Yeah. And then, you know, if you're adventurous, you can do 3, 1, 2, 2. So this is 3 minus 1 over, and then it's 1/3. Right, and generally R1, 2, 2, 2 with R minus 1 factors is the same calculation. Right, so remember when I do R over R minus 1, I get 2, 2, 2 R minus 1 times. Right, that corresponds to a picture that looks like this. Sorry, a picture that looks like this that I've drawn several times already. So if I do Z2 plus Z times 1 over R of 1 R minus 1, this is the thing that happens when I do the resolution of the simple quotient singularity xy equals, I get this. Whereas on the other hand, if I do 1 over R of 1, 1, I get this picture. And this again is sort of relevant to the quotient singularity. Okay, so why is this true, and how do I do this calculation? So the point is to do these, to put both of these calculations in one and the same picture. Right. So here I'm doing now. Which way round am I going to do it? So if I start off here with 0, 1, and then I have these guys going down there to 1, 0, then this is, 1 over r of 1a, right? So the thing we're talking about here is the lattice Z2 plus 1 over r of 1a, z times. Yeah? So this is an over lattice of Z2 with this extra bit added to it. So it's a lattice. And so in the lattice, together with this vector, there is minus this vector, right? Which is the vector minus 1 and then minus a. Right? And I can go down from this vector by this amount. So there's also this vector there. Right? So this is I think I'll just not bother to write the 1 over r's anymore. So this is minus 1 and then r minus a. Okay, 1 over r of this. Right? And the point is that this is a parallelogram. Yes, it's a parallelogram. So just by construction, I take this vector here minus this vector and to get this point, right? And so the sum of these two vectors is that one, right? And then so here are these points here that are, so the formation of this Newton polygon. Polygon is 1 over r, is the continued fraction expansion of r over a. This is the b1, I'm not quite sure, L minus 1 I think I had. And if I try to do the same thing with the continued fraction here, this is 1 over r of, this is r over r minus a is b1. Right. And, this vector here at the end, this vector is minus 1, 0. That's exactly minus this vector here. Right? And so what I've got here is I've got the upper half plane in the lattice L, and I've got it broken up into basic triangles. Right? And each of these basic triangles is like this. Right? Each of them has, so each of them is just the basis. We're doing SL2Z geometry here. Each of these two things forms a basis, and passing from one basis to the other involves this B1 up to BL minus 1, and down here goes. And at the end of it, I get that this vector is equal to exactly minus this vector. Right? And so that's this 0 on the right-hand side here. Right? So the upshot here is that if I do so I'm just going to read this continued fraction. If I do 0, 1 minus a k minus 1, 1, and then 0, 1 minus a k minus 2, 1, and then I continue here down to the middle where I get 0, 1 minus a 1, 1, and then I do 0, 1 minus 1, 1, right? The 1 corresponds to this parallelogram. So in each of these little intervals here, this guy here multiplied by his corresponding tag is the sum here. So to be compatible with what I do in the middle here, I want the tag here to be 1. This guy here is equal to 1 times these two. So it's saying this picture here is convex everywhere, except there's just one place where it's not convex, and there it's got this 1. Right? So if I do this 0, 1 minus B1, 1, 0, 1, minus B2, 1, and so on, all the way up down to minus B L minus 1, right? This is the change of basis, which goes from this basis to this basis here, right? So I start off with this basis. Changing the basis here is this first matrix. Changing each successive matrix until I get to there are these matrices. And then this matrix here changes the basis from this to there. And then it goes on down there, and eventually I'm going to get down to just one step beyond there. Right? And so this matrix will be minus 1, minus 1, 1, 0. Right? And this 0 here is the continued fraction. Okay. So there are kind of a couple of little tricks that you can do here, which mean that you don't actually have to calculate these products of matrices. Right? I'm saying this because I'm going to need it. I'm going to use it very much, very often in the lectures in 2 weeks' time. So notice, if I do 0, 1, minus 1a, product 0, 1, minus 1, 1, product 0, 1, minus 1b. So I'm doing this continued fraction here with an a, and then a 1, and then a b. Right? That's the same thing as 0, 1, minus 1, a minus 1 times 0, 1, minus 1, b minus 1. Right? This is just an identity in matrices. So, do the calculations, just multiply out the matrices. Left-hand side is equal to something, right-hand side is equal to something, and you'll get it immediately. Right, so they're both equal to, what are they? I think it's minus 1, a minus 1, b minus 1, or maybe it's minus, I don't know, ab minus b, minus a minus b. So this is something to do with a minus 1 times b minus 1 minus 1 is ab minus ab. Okay, so this is just some kind of mumbo jumbo. On the other hand, if you think about this picture here, then I've got the upper half plane broken up into, incidentally, the calculation I did there says you can go from here to here directly, right? I can take the 2, 1, 2, I can cross out the 1, and I can reduce the two guys left and right by 1 each. I get 1, 1. So, on the other hand, I want to say that this is sort of something that's in some ways geometric to do with this picture. So, this picture, in each of the two octants, inside the two octants, the picture is convex. It bends downwards. It's only allowed to bend downwards. Right? There's just one place where there's an exception, and that guy is there. Right? So think about the upper half plane. The upper half plane in Z2 is a certain semigroup. These convexity properties are to do with generators of the semigroup. Right? So this guy here is the sum of these two guys. So we don't need him as a generator. So let's decide we're going to chop off his head. Yeah? So when you do that, Now I try to understand how this point is related to these two. Sorry, how this point is related to this one. And so, you know, because I'm now so the guys out here haven't changed, but the tag at this guy has decreased by -1, and the tag here has also decreased by -1. And moreover, unless we've completely finished already, this tag here also has to be 1, because, you know, this picture can't be convex everywhere, because it's sticking out, right? So there's a tag of 1 here. Okay? So let me do you know, my favorite example again. So you know, I had 19 over 8 is, try to get it right this time, 3, 2, 3, 2. 19 over 11 was 2, 4, 3. Right? So my recipe says, write down 3, 4, 2, 3, 2, 3, 2, and concatenate them with a 1. Right? Then this continued fraction is 0. Okay? And there's a little calculation here which is very, very easy, just based on this idea. So I'm going to take, I see the 1 in the middle, right? So let me underline him and his two neighbours, right? And I'm going to cancel the 1 and decrease each of his neighbours by 1. So that's the same thing as 1, 2. Right? And I'm going to cancel this 1. So now I write down 4, 1, 2. I write down 4, 1, 2, and this is now 3, 1. I bring down this 2, and I cancel this to get 1, to get 2, 1. Right? And I'll bring down this 3, and I cancel these again down to get 1, 2. Okay, and now I've got 3, 1, 2, 2. So when I cancel this, the 2 goes down. I cancel this, the 2 goes down. I get down to these things. Right? This is 3, 1, 2, 2. That's the thing I have there. Okay. So this calculation is going to appear many times. It's a very simple thing, and it's very easy to understand why it's true. It's not completely clear why it's effective when it's, you know. So another expression of the same thing called Riemann-Schneider staircase. So I'm just going to do it in this example because it's. So a staircase is something that looks like this. So what I'm doing here is I'm looking at this fraction. I say 2, 4, 3. So I'm going to do 2 minus 1. So here I have step down. Sorry, I'm going to have 2 minus 1 nodes. Right? So that's no step down. Right? So here I'm going to have 4 minus 1 nodes. Right? So there's 1, 2, 3 nodes here. I'm stepping down by 2. Right? And then each time I step across by 1, the gap, these commas here, the gap between the 2 and the 4 and the 3, I just move across by 1. Right? And here I have, I'm sorry, I should have had another one there. 3, minus 1 nodes. Right? And so this thing here is just a way of writing these numbers, 2, 4, 3, in a kind of pictorial way. Right? And I'm going to think of the picture not going down but going across. And so here I'm seeing 3 nodes. Here I'm seeing 2 nodes. Here I'm seeing 3. Here I'm seeing 2. Right? So you know, I mean in the example that we had with R steps here forming an arithmetic progression down the line here. This corresponds to 1 over R, 1, R minus 1, and then versus this thing here with only 1. This corresponds to 1 over R of 1, 1. Right? So the thing you're seeing here is a very big number here. There's a single tag of R, and here there's R minus 1 tags of 2. So it's a particular case of this picture. Right? If I look at it one way, I'm seeing R minus 1. I'm seeing R minus 1 tags. If I'm looking at it this way, I'm seeing a little sequence of R minus 2 nodes. Whereas if I look at it, R minus 1 nodes corresponding to the number R. So here R corresponds to R minus 1 nodes. Right? And here I'm seeing there's no step down here at all, so I'm seeing 2 minus 1 times R minus 1. So these 4s here, the big number here, 4, corresponds to a little sequence of 2s. If I had 5 here, I'd have to have 3, 2, 2, 3. Right? The big number here corresponds to a little sequence of 2s. Okay, so this is just combinatorics. So, you know, do some numerical examples. Read what it says in my lecture notes and do the examples. Okay, so I want to explain about discrepancy calculation. And I'll start off by doing it in simple examples in 2 dimensions and then assert that basically the same calculation works also in higher dimensions, in any dimension. So, so my situation here is I've got C2, which I'm thinking of as a certain manifold, divided out by a group action to get X. So there's a group acting here. It happens to be the cyclic group of order R here. And then here is a resolution of singularities. Right, and so the discrepancy is I want to compare Ky and Kx. So this is only going to make sense. Kx will be Q Cartier divisor. I'll explain what this means in a minute. And so I'm going to do F upper star Kx. So, you know, somewhere here there's canonical class and differential forms and Grothendieck dualizing sheaves and things like that, right? But I'm writing F upper star here. It's F upper star of a Q Cartier divisor. However, whatever it is, this must coincide with Y, where Y and X are isomorphism. So this is, in particular, this is birational. Right, so there's a big locus where this is just Y and X are isomorphic. So I must be able to compare Ky and Kx. And what I'm going to write is Ky is Kx and then plus sigma Ai. Ei. Right, so I explained the resolution of singularities is given by this picture in Z2 plus Z times 1 over R 1A. so I've got E1, E2, L minus 1, right? So the EI correspond to the vectors EI, when the discrepancy is essentially the distance below the diagonal. Right, so it's minus the distance below the diagonal. So if I write down a fifth of 1, 2, for example, you know what singularity this is. So the theorem says that its resolution looks like this, minus 2, minus 3. So the resolution is, the thing I've done here is 5 divided by 2. 5 divided by 2 is 3, 2. Maybe I should write 3, 2 in the opposite order. And the canonical class will be if I get it right, right, so in this case I have these pictures like this, right, and I'm saying that you measure this distance, you calculate this distance, you calculate this distance, and the distance at this point here is below the diagonal, and that's the number that comes here, and then the same here. Okay, so this is just formally how you calculate it. Let me explain what it means. And so, discrepancy. So, I have, I think of it as the divisor of a Jacobian determinant. So, to just try and understand this in the simplest possible case, here is C2 mapping to C2. Right, this guy's got coordinates x1, y1, and this map is given by xy, x equals x1, and y equals x1, y1. Right, so, I'm just saying, I'm taking, here I've got an ordinary copy of C2, I've got this point here with coordinates xy, and then I'm allowing myself to write y1 equals y over x as birational coordinates. Right, so this is just the ordinary, usual blow-up of P in C2 and then restricted to an open. Right, so there's a map here. There's a morphism there. So F defines in a canonical way a homomorphism from something to something. Try and remember what. So if I write down df, I think it's taking f upper star of omega 1 of this. So let me call this x and y, that's above. X maps to omega 1 of y. Right? And this is basically just a Jacobian matrix. right? So I told you what the coordinate transformation is, right? So x1, x and y are some functions of x1 and y1. So I can write d by d, and here write x, y, and x1, y1. Right? I'm doing a complete trivial calculation so that you can see that this is a very simple idea. Right? Differentiate x with respect to x1, you get, so this is something like, I don't know, dx equals dx1, dy equals, so it's x1, it's x1 dy1 plus some term I'm not interested in, y1 dx1. Right? And so if I do dx wedge dy, this is x1 dx1 wedge dy. Yeah? And so, you know, this x1 here, the coefficient x1 here is the Jacobian determinant. It's the determinant of this matrix. Yes? And so this is saying, when I do a blow-up here, I'm getting ky equals kx plus b. So this is a formula everybody knows for the blow-up of a non-singular point on a surface. Right? And this E is the discrepancy. So it's sort of tedious to do this in general for these singularities, but let me just say, let me just give another example now. So I'm going to take a third of 1, 1. Right. So here I have, you know, C. So x is singular, so it's sort of not really clear who is kx. Instead, let's start off with C2. So on C2, C2 is the free module generated by du wedge dv. I mean, if you want, it's OC2 times du wedge dv. So my group action here is multiplying each of u and v by primitive third root of unity. And so this guy here is not invariant, not mu3 invariant. And I want something which is mu3 invariant. So I'm going to write down du wedge dv raised to the tensor power 3. So whatever else this is, it certainly is mu3 invariant. Right, and it's a section of OC2 of 3 KC2. Okay, so this should, so because he's invariant, he should descend to the quotient. So the way to see that he descends to the quotient is just to choose something on the quotient which is obviously right. Right? And so you need to do a bit of experimentation here. What I'm going to do is write down dx naught wedge dx1. These are these guys here. Right? And I'm going to raise this to the third power. Right? Because this one was raised to the third power. So, you know, this is sort of something quite like this guy here, except that he's got a lot of u's in him. And he's got a lot of spare u's. And so it turns out that what I should write down here is x naught to the power of 4. I'll explain afterwards that you can do this without experimentation. You can do it in a kind of completely automatic way for any toric variety, but at the moment I'm just doing it ad hoc, right? So figure out who dx naught is, right? So this is 3 u squared du, and d of x1 is a term I'm not interested in, namely 2u v dv du, and then plus a term I am interested in, which is u squared dv. Right, so when I wedge the two of these two together, I'm getting 3 u to the 4th du wedge dv. Right, and that's sort of basically the same as the guy I said at the beginning, except he's got multiplied by this eigenfunction. Right, and so I want to divide out by this u to the 4th, but unfortunately u to the 4th is not a function here. Right, u to the 4th is a function upstairs that's not invariant under mu3. And so again, in order to make this invariant, I'm going to take the third power. Right, so if I take the third power, I get 3 cubed. This is just a non-zero constant times, and then u to the 4th. So now this is x naught to the 4th. Now, and then it's du wedge dv cubed. So if I do this thing divided by x naught to the 4th, there's this harmless little scalar factor there. And then this thing is, so this is a constant scalar factor times du wedge dv cubed. So if you look at this thing, what is he? Well, he's one of these, he's a section, he seems to be a section of omega 2 of x, tensor 3, and then possibly with pole. Yes? However, when you lift him up there, this guy here, which is written down here as a rational differential in these invariant quantities, just becomes equal to this du wedge dv tensor 3. Right? So if you ignore the origin, then this guy here, du wedge dv is just a basis for the canonical class of C2. Du wedge dv all cubed, tensor 3 is the basis for that tensor 3. The map here is étale. The map is unramified, so the Jacobian determinant everywhere is invertible. So omega 3 here and omega 3 there are just related by pullback under a covering map, under an unramified covering map. Right? So you can see that also that this guy, so I'm going to write S for this guy. That also S equals, so there's a constant scalar factor here, which is probably plus or minus 3 to the 4th times dx2 wedge dx3 divided by x3 to the 4th. Sorry. Right. So here I have something which has got x naught as a pole. Here I've got something which has got x3 as a pole. And these locuses don't intersect. So this thing that I'm writing down here, I wrote him down originally with this pole in order to get something that looks like du wedge dv cubed. Right? But actually he can be written down on any other open piece of the variety except for the origin. And so this argument says that, therefore, the sheaf omega 2x tensor 3 on x non-singular extends as a line bundle. So I can find one single section of this bundle, namely this guy S here, which is a basis for this line bundle everywhere except for the origin. And so if I just take, if I take S here, so the thing I'm going to say is that OX of 3kx is equal to OX times S. Okay, so outside the origin, this is proved by the formulas. And then at 0, it's basically a definition. Right, or it's the property that this is a divisorial sheaf. And so it can't, these two guys have to coincide. Right. And so, you know, I asked earlier who is kx. And, you know, I'm going to say I don't really know who kx is. On the other hand, I do know who 3kx is. So 3kx is the Cartier divisor, is S. Right? The sheaf OX of 3kx is the sheaf generated based by S. It's a locally free sheaf generated by S. Right? And so now it makes sense to say that 3ky is 3kx and then plus A times Z. Right? And the question is, who is A? Who is this A? And the answer is A is minus 1. Yes? So so let me explain how to calculate that. So you know, the board's a bit messy. So here I had du wedge dv. Right, downstairs I had this S, which is dx0 wedge dx1 over x naught to the fourth. Right, and so here, if I take this resolution, so the resolution has coordinates y0, y1, let's say. Sorry, let me write. Let me write y0, y1. Right, here y0 is x0, and y1 is x1 divided by x0. Right, so now there's a little Jacobian matrix calculation saying that this S in y0, y1 coordinates is dy0 wedge dy1 tensor 3 and then divided out by y0. Okay, so when I take the dx0 upstairs, I get y0. When I take the dx1, I get this x1 divided by x0. So I do get rid of three of these denominators when I do the dx1 over dy0. However, there's still one denominator remaining, and that's this y0. Right, and so you know, the picture is, here I have 0, 1, here I have 1, 0, and here I have the point 1/3 of 1, 1, and his distance below the origin, below this diagonal line, is 1/3. Okay. So I'll explain. This is just a baby example, so you can really understand what's happening. I'll explain a little bit how you do this in more generality for general.